Okay, so I'll start the recording, and hello everyone. And thank you all for joining today's TVS Science Colloquium. So let me start by reminding you that this talk is being recorded and will later be uploaded to the TVS YouTube channel. After the presentation by our speakers, there will be plenty of time for your questions, so please save them until the end of the talk or type them in the chat. And now I would like to give a very warm welcome to our speakers today, David Buckley and Russ Taylor, who will present to us the BRICS Intelligent Telescope and Data Network. So David here is based at the South African Astronomical Observatory and was the SALT project scientist during the design and construction phase. Then he was the first SALT astronomy operations manager and also the SALT science director. After obtaining his PhD from the Australian National University, he took a postdoctoral fellowship at the University of Cape Town, and then he moved to South African Astronomical Observatory in 1991. His research has mostly focused on compact accreting binary stars, including X-ray binaries and cataclysmic variables, and more recently, David has focused also on astrophysical transients, where he is the principal investigator of the SALT Transient program and the South African affiliate PI on the Vera Rubin Observatory's LSST. He is also an investigator on a number of international projects, including leading BRICS. So this is the Brazilian, Russia, India, China, and South Africa Astronomy Initiative to establish a flagship program on astrophysical transients and big data. In recent years, he has also assisted in astronomy capacity development in other African countries, including Ethiopia and Kenya, where he has been involved in projects to establish optical telescopes for research. And our second speaker today is Russ Taylor, who is currently the director of the South African Inter-University Institute for Data Intensive Astronomy and a South African Joint Research Chair in Radio Astronomy at the University of Cape Town and University of Western Cape. He obtained his PhD from the University of British Columbia and moved to South Africa in 2014. He has served on numerous national and international committees and boards, and among these are several that impact planning and development of astronomy worldwide, including president of the Radio Astronomy Division of the International Astronomical Union. He has played a leading role on square kilometer array projects since its inception, serving as a founding executive secretary of the International Square Kilometer Array Steering Committee, founding chair of the International SKA Science Advisory Committee, vice chair of the International SKA Science and Engineering Committee, and as a member of the International Board of the Preparatory Phase Program for the SKA and of the International Board of the SKA organization. His research has mostly focused on radio astrophysics and the techniques for radio imaging of the sky. So David and Russ, please go ahead and give us this introduction for the BRICS.
Thank you for that very comprehensive introduction, Katja. Yeah, so the talk will be in two halves. I'm going to talk for the first 30 minutes or so, covering the transient and variable side of things, but also giving a background of the whole BRICS astronomy, and in particular, how we got to this flagship project. And I'll also be touching on one aspect of the program, namely the societal benefits program. And then I'll hand over to Russ, who will talk about the big data survey science aspects. So let's see, hopefully it will advance. It was. Go to my next slide, I hope.
It hasn't actually gone to your next slide.
No, I see that, and I don't know why, because it was working fine. Oh, I think it's waiting for me to respond to something. Sorry about this. There we go. So BRICS, as the name suggests, is a collection of 5 countries, a sort of a community involving Brazil, Russia, India, China, and South Africa. And they have economic ties, cultural ties, trade ties, but they also have a program to develop science and technology in the different countries and in collaboration with each other. And within the science goals, astronomy features quite strongly because, as you know, all 5 countries are doing compelling research in astronomy. They have their own facilities. So there's a lot of, I guess, goals that are shared between the countries, and a belief that if we collaborate together, we can possibly do things, more things than we could if we were just doing it on our own. So the program I'm going to be talking about today leverages the existing facilities which we have within our own countries, but also for which BRICS or individual countries may have access to. So, for example, in Brazil, they have access to telescopes not owned by Brazil, but operated by other observatories or countries, examples being the SOAR 4-meter telescope and also Gemini. So this project that I'm talking about, Russ and I are talking about, came out of an idea to have what we call a flagship program, something that would be on a scale larger than traditional collaborations. And it focuses on the big potential of big astronomy survey programs in the next 2 decades and the enormous data that will be produced and the challenges that they bring in terms of computations. And those 2 programs are in fact in the optical, the Rubin Observatory's Legacy Survey for Space and Time, and in the radio, the Square Kilometre Array. So here are some nice images. This is a bit out of date, obviously. It's a lot more complete looking now, the LS Rubin Observatory. And this is an artist's concept of the Square Kilometre Array, of which the mid-frequency dishes are being constructed or will be constructed in South Africa. And Meerkat, the existing 64-dish array that's been operating since 2018, will be part of that phase 1. And I no doubt Russ will be talking more about this in the future. So as I said, this program is exploiting existing facilities. So here's some pictures of some optical telescopes in our respective countries. So all of these telescopes, plus smaller ones, are envisaged to be harnessed in this program. And here is the similar slide for the radio facilities, and Meerkat that I just talked about, you can see there on the left. GMRT is the giant meter wave radio telescope in India. FAST is obviously the big dish in China, and then a few smaller dishes in Brazil and Russia. So just in summary, we have access to these up to 10-meter class telescopes, including SALT, but also 4-meter telescopes, a new telescope that was recently commissioned in India, the 3.5-meter Aries telescope, a 4-meter liquid mirror telescope, which will, I believe, is still undergoing commissioning in India, which will be a transit survey telescope, and then various other facilities that I've already mentioned. And there, again, is an artist's concept of what SKA phase 1 might look like when it's completed in the late 2020s. So the history of the flagship project grew from this science, technology, and innovation program, which began under BRICS several years ago. But that program basically funded fairly small scale projects. They were limited to 2 to 3 year duration. They mostly only supported research collaboration visits and the holding of meetings. And so they were fairly modestly funded at a level of roughly about $20,000 per year per partner. But in 2017, the Astronomy Working Group of BRICS made a decision, a strategic decision, to develop what's called a flagship astronomy project. And this was envisaged to be something that would be compelling and competitive internationally. It would involve most, if not all, of the BRICS countries, ideally. And what followed from that was a call for a concept note proposals. These were received in 2018 and reviewed at the next BRICS Astronomy Working Group meeting, which was held in South Africa. And what came out of that was basically reviewing all of those proposals under criteria that are all listed here. Those most important ones were how much impact they would have, how scientifically competitive and unique would these projects be, what was the potential for participation by all of the BRICS countries, what were the socio-economic benefits that might be leveraged from these programs, particularly in terms of HCD, developing young researchers and scientists and technologists, how it aligned with the fourth industrial revolution paradigm, potential for private sector involvement, and leveraging both existing but also future planned national facilities. So what came out of that was an assessment of all of those programs and a sort of realization that many of them were similarly themed, those concept notes, which were quite short concept notes. I think they were limited to just 5 pages. The next stage was to basically bring together the different parties who had interests, common interests, and develop full-fledged proposals. So, for example, in the transient area that I led the proposal on, there were 2 other groups who also had interests in transients and variables. So in the end, 3 of these proposals came together into a final transient and variable proposal. Likewise for Russ, his project on big data in the era of SKA, there were, I think, a total of 4 different concept notes of a similar theme, and they were brought together. And then likewise for the 3rd theme, which was in neutral hydrogen cosmology. And so the final result, there was 3 separate proposals that went to a full proposal phase. And at the next BRICS Astronomy meeting, these were assessed, and in the end, it was decided not to just approve one of them, but to meld the 2, number 1 and 2, which was the transients and big data, together. And so I guess you could say that Russ and I were subjected to a shotgun marriage by the BRICS Astronomy Working Group to say, okay, you can work on this proposal, which will cover the different aspects. And so that's what happened. And this proposal has now gone ahead. The opportunities for this flagship program are listed here. And as already mentioned, it includes the synergies with existing and future development. But very importantly, the opportunity for development of human capacity development, postdocs, postgraduate scholarships, having students move between the BRICS countries, potentially having visits and co-supervision, having annual meetings and workshops in thematic areas. And that's all what is now encapsulated or was encapsulated in the final proposal, where the budget included, for example, the funding of something like a dozen or so postdoctoral fellowships and student bursaries. Also, the technical collaboration opportunities were in the area of telescopes and instruments, and I'll be talking about that in particular with the transient and variable star science, but also fourth industrial revolution, machine learning, big data, artificial intelligence, which Russ will talk about. And then the wider benefits to society. Any big program internationally these days needs to address this, and I'll briefly talk about that at the end of my talk. we also took a sort of practical, pragmatic approach in terms of how we envisage this program developing, and in particular, the funding constraints that we're all under. So we have a model where we use existing facilities and ramp up as money becomes available to expand and do the things that we want to do. So a lot of initial effort is going on the networking of existing telescopes for more efficient automated response to alerts. And of course, that's why we're talking to the TVS, because this is very close to the heart of the science that, of course, we do within TVS, and indeed other collaborations within LSST, Rubin Observatory. So a lot of what we're thinking about at the moment with regard to efficient follow-up is the what and how of follow-up. In other words, what targets and what type of observations are required. And so obviously we're learning from the experiences with other groups, for example, the growth network that follows up on ZTF and other transients. So it is a somewhat challenging project in the sense that we have quite a heterogeneous collection of telescopes, all with different operating systems, some of them dating back a long time, but it is tractable. And so this is the way forward. And just in summary, this is the major investigators on the project. So Russ and I are the co-PIs for South Africa, but every other country has 2 PIs as well, covering the transient variable time domain astronomy and the big data survey science respectively. But there's another over 100 co-investigators as well. So it's a big program, and it really has just kicked off. It started last year, and I'll talk a little bit more about how it's going shortly. So for the transient aspect, time domain astronomy, transient astronomy, I don't think I need to convince this audience the importance of this, and looking at the variability timescales of objects, and of course leveraging what is going to come out of LSST, which is this wonderful data set of 10 years looking at the southern skies. So transients obviously cover many different classes of objects, from the closest solar system objects to the furthest gamma ray bursts and the most energetic things. And to some extent, our plans for how we will do the follow-up in South Africa has been guided a bit by the experiences with the SALT transient program, which I've led since 2016. And this is also a multi-investigator program covering a wide range of different objects, and some of them are listed here. And these are where various groups within the collaboration have specific interests and drive the science in these different areas. And the flavors changed over the years, because when we started off, it was before the first detection of gravitational waves. So multi-messenger astronomy, which encapsulates GW events and neutrino events. These are things which began in 2017 for us with the GW 1708-17 event, where we got spectra from SALT 1.2 days after the event. More recently, we've also been following up on transients from Meerkat since it began its operations as well. So in terms of developing the network of telescopes within BRICS for the transient follow-up and variable follow-up, we're leveraging a project that began a couple of years ago here in South Africa, which is the aim is to basically utilize many of the telescopes on our observatory plateau, potentially up to 11 different telescopes there. Some of them belong to us, so we have the rights to decide how we use these telescopes. Other ones we have access to and time on those telescopes, examples being the Las Cumbres Observatory network of the 3 1-meter telescopes that are there. So this project is at the moment working along the lines of turning all of our own telescopes, the SAO owned ones, like the 1.9 meter, which dates from 1948. It's a very ancient telescope, but it's now able to be completely remotely and soon robotically controlled, as are a number of 1-meter class telescopes as well. So this is ongoing work, which South Africa is putting a lot of effort into, and I might add that it's also something which is going to benefit the wider LSST community, because our in-kind contribution to LSST will include the potential for access to telescopes at SAO and SALT, in fact. The next phase, which is the more ambitious phase, is to develop a network of new telescopes, and in particular, a network of 1-meter telescopes throughout the BRICS countries that would enable us to do all sky monitoring. In other words, all 4 pi steradians of the sky, with a cadence that would be at least an hour from an array of telescopes distributed in a longitude and latitude. So this is a fairly ambitious sort of project, as you can probably appreciate. The idea to survey over 5,000 square degrees an hour with a half-hour, 1-hour cadence in 3 colors, G, R, and I filters, and have it as a 24-hour operation. And so within the current BRICS program, our effort at the moment is more in the area of exploring design phase space for such telescopes, not to fund necessarily the construction of all of those telescopes which would be needed for this very, very ambitious program. But what I should mention is that there are already projects that began within BRICS, particularly by our Chinese collaborators and our Russian collaborators, to build wide field 1-meter class telescopes for this sort of follow-up of transients and variable objects. So here are just some optical design of various proposed telescopes, which back when the project was first put together were just concepts. This is the Citian concept to have, which is the Chinese driven one, which is to have 71-meter wide field telescopes, each with 25 square degree field distributed globally. And they want also 2 or 3 4-meter telescopes to do spectroscopic follow-up. This is a very ambitious program, as you can probably appreciate, but it is headed towards being a major new infrastructure project in China if it gets approved in the near future. Nonetheless, there's a lot of money already being put in by the Chinese to build prototypes. And in fact, here is a picture of some work that's being carried out in the Nanjing Institute of Astronomical Optics and Technology, where they're putting together a first prototype. These wide field telescopes, and also this is an example of one design which the Russians have been pushing for a similar wide field telescopes. And they all leverage as detectors large format CMOS detectors. So here's an example of 9K and 6K CMOS detectors, which are envisaged to be used on these wide field telescopes. So this is the future, the stage 2. And just to summarize the benefits of this flagship project to BRICS, it ticks all of the boxes in terms of what a flagship should do. So it's promoting collaboration within the BRICS countries. It has a large component of capacity development for young researchers. It will support multi-messenger astronomy, following up of electromagnetic counterparts. And in fact, a program that's going to start this year will harness the facilities specifically for the 04 Advanced LIGO Virgo CAGRA campaigns when they begin. It also has the potential to expand and collaborate globally. So we're hoping that this will be of interest to potentially people in the audience, people involved with LSST, to work together on this. And it will harness existing and future multi-wavelength facilities, both in all of our BRICS countries, not just ground-based, but also space-based as well. So I'm just going to quickly summarize what the project is expected to cover. I mean, basically, we're hoping to fund regular meetings and joint technical meetings, thematic meetings, research collaborations. As I said earlier, we hope to have postdoctoral and postgraduate fellowships. We are also developing software for the integration of the networks of telescopes. So we're hoping to hire software developers and do design studies on the 1 meter telescopes, and possibly even fund some prototype development. So the cost of this, we've estimated at around $30 million, which is for this program, which is to last something like 8 or 9 years. It sounds a lot, but you know, per annum and per country, it's I think a perfectly reasonable amount to expect if indeed the BRICS countries are committed to do something like a flagship. Last year, seed funding from South Africa was provided to start the whole program, at least in South Africa, and that's funding 3 positions: a project coordinator, a software developer, and a big data scientist. And we're expecting that future funding from the other BRICS countries will kick in, we hope, in the not too distant future. I'm going to now just finish the my part of the presentation with a brief mentioning of the societal benefits. So the science goals of this program, as I say, are well stated. They're well motivated in terms of transient, variable, and time domain astronomy, which I've spoken, well, not very much detail, but spoken to. And the big data, big compute for survey science, which Russ is going to speak to next, are the 2 main science pillars of the program. But an equally important pillar is the societal benefits projects. And so we have on our team people who are used to working and developing these societal benefit programs. A large component will be in human capacity development, but it's also tied to the potential for projects that address the UN Sustainable Development Goals, the SDGs. And this little graphic at the bottom highlights in the bolder boxes those Sustainable Development Goals where we believe we could have programs that impact on that. And basically the themes that we're covering within this societal benefit aspect is, of course, the human capacity, the training of young scientists, engineers, and technologists, the bridging with industry. So clearly there's a huge potential in terms of compute and big data, but also in the development of mass production of telescopes and cameras for the wider network of telescopes to detect transients. Public science awareness is a big aspect. Development of communities through programs like the IAU Office for Astronomy for Development run. There is a significant sort of component addressing the theme of life on Earth, because it's expected this network and in fact, one of the drivers, science drivers of the network is the detection of potentially hazardous objects. It's a strong theme from our Russian collaborators to detect, as Atlas, the network that's run by NASA, detects potentially hazardous near-Earth objects. And of course, what's developed in recent times is how the sort of skills and techniques that we do in this program maybe have an impact on the way COVID-19 is investigated, or the sort of processes that might be utilized in that. And finally, before I hand over to Russ, I just want to also mention that there is also now beginning within Africa, and this is where I'm wearing my hat as the chair of the science committee of the African Astronomical Society, that we developed this concept last year of an African integrated observation system, which would be like a small version of the BRICS program, because of course in Africa, the sort of facilities are not as extensive, and some people might not realize that there are still compelling facilities. And so our idea is to expand the intelligent observatory concept that's happening in South Africa to include telescopes and include observatories within the African continent. And you may appreciate that there is a significant research observatories in other African countries like Morocco, Egypt, Algeria, more recently Ethiopia, with 2 1-meter telescopes being developed there, and the potential for future telescopes being developed as well. So this is something as well where we hope that maybe through international collaboration in transient and time domain astronomy, that the science research capacity is increased within Africa, which is sorely lacking at the moment. So with that, I complete the first part of my of this presentation, and I'll hand over to Russ, and I think we'll be taking questions jointly at the end of the presentation that Russ is giving. So I'll just stop my sharing so that Russ can then share his presentation.
Thank you, David. I will just share. So I presume everybody is seeing my first slide, the BRICS ITDM.
Yeah, we can see it. Good.
Excellent. So David gave an outstanding introduction to the project. So some of what I have to say I can go over very quickly. But I'm going to talk about the big data and survey science aspect of the project. But I should point out that in being part of this shotgun wedding with David's Transient project, it's been an opportunity to think about the synergies between the big data solutions that we're thinking about for survey science and the big data challenges in transient science as well, which are not inconsiderable if the facilities that David talked about become reality. There's a tremendous data challenge associated with that as well. So the original proposal for the big data and survey science grew out of the involvement in several of the BRICS countries in the Square Kilometre Array project. China, India, and South Africa are all longtime members of the Square Kilometre Array organization and have invested substantially in major facilities, which are pathfinders and precursors for the SKA, and the development of the concept of regional centers for the SKA, which would be the sort of the network, which is the data engine of the Square Kilometre Array project. So there's a common interest of at least 3 BRICS countries in moving forward on the big data challenge associated with the Square Kilometre Array. But if you dig deeper into the 5 BRICS countries and ask what are the data-intensive facilities that are being challenged by data. Beyond the SKA, in Russia, there's the Pashino Observatory, which is a low-frequency wide-field imaging telescope, which is addressing many of the challenges that the low-frequency part of the SKA will confront. Most of the countries also have an interest in very long baseline interferometry, and advances in VLBI are presenting us with a data challenge as well. And of course, also several countries are involved in the LSST. Brazil quite strongly, South Africa quite strongly. So there is a landscape of big data astronomy emerging in all 5 of the BRICS countries, driven by the large wide field imaging capabilities in survey science of the next generation of facilities. I mentioned VLBI. It's sort of a special case. What's happening with VLBI is traditionally VLBI has been a very narrow field enterprise where you bring together heterogeneous telescopes from around the world to observe a very small object at the center of your imaging field. Over the last 5 to 10 years, wide field VLBI is beginning to become a norm. And what I'm showing here is a project being done with the VLBA and run by NRAO in the US by a team in South Africa, which is mosaicing many fields observed in VLBI mode to make a large image of a fairly large region of the sky with extremely exquisite resolution, and million arc-second resolution. So these are producing terapixel scale images, and as a function of frequency. So these are very, very large data sets, and they are precursors of the second phase of the SKA, which is going to be basically a VLBI instrument, baselines of several thousands of kilometers, producing extremely high resolution images. So lots of things are happening. What I'm showing in this plot is a plot of the growth of data in radio astronomy. And you sort of see 2 phases in this plot. There's a phase that ended around 2018, which was largely driven by facilities in North America, VLA, the JVLA, the Arecibo telescope. And this is a log linear plot. The blue line is the growth in data to astronomers with a doubling time of about 2 years. The red line is what we're now confronted with the next generation of radio facilities. A much faster growth of data. The doubling time for this data is like 8 months. And you see many of these, several of these, most of these projects, in fact, are projects that involve BRICS countries. So we are confronted with a very large data problem, which we're just at the beginning of this curve, but it's growing rapidly. At the same time, the way that radio astronomy or astronomy is being done is changing around the world. The LSST is a great example of this. That instead of individual PI-driven projects, you have these large, unique global facilities which are serving a global community, and they have identified high-priority science areas which are basically large amounts of observing time are being devoted to. And that data, and that produces these large amounts of data, and we need to find ways to enable researchers from around the world to work on that data when individually they can't have the data on at their own facility. So it's a different paradigm for doing astronomy, and that's sort of the framework that we're working in. So just mention some things happening in South Africa, which are relevant, sort of a leaping off point for the BRICS collaboration. Meerkat telescope is basically working in this new paradigm of large projects, large high priority projects. So we have what are called key science large projects on Meerkat, which is taking about 65% of the observing time over the 5-year lifetime of Meerkat before it comes rolled into the SK mid frequency telescope. 3 of those are time domain projects. The bottom 2, TRAPPIST and Meertime, are pulsar projects. Thundercat is an interesting imaging transient project, and the The top 5 are basically imaging projects for continuum or atomic hydrogen emission from fields in the universe. So these projects generate large amounts of data. They are all international collaborations. This is the distribution of researchers involved in large survey projects. 22 countries, 121 institutes. They are basically the beginning in radio astronomy of the new way that we're going to be doing radio astronomy in the coming decade. So confronted with this sort of situation, we have the challenge of going from data to knowledge in multi-wavelength survey astronomy. And I've broken this down into sort of 4 thematic challenges. One is, how do you collaborate and share and execute projects internationally with distributed teams around the big data being produced by these projects? Second one is the sheer problem of how do you manage the data? We in radio astronomy, radio wavelengths alone are only a small part of the picture. We really rely on multi-wavelength information to carry out our science programs. So we need to merge and fuse the radio astronomy data with data from other wavelengths. And the LSST is perceived as one of the key sources of information. And we need to empower end researchers. We need to find a way to empower people to work on that data and to apply things like artificial intelligence and other analytics approaches to this data set. And so these are the challenges that we're trying to confront, both in the SK community itself, but also now within this BRICS ITDN project. So we think that cloud computing is a key component of the infrastructure approach to solving this problem. It allows for platforms to build collaboration. It allows for allocation of resources matched to the scale of a problem, and it allows researchers to interact with data on a platform from any location. We've built a cloud in South Africa in my institute, which is being used for the Meerkat Large Survey project. And I won't go into details of this, but all of the technology smarts are in the dashed box on the left, and the user interfaces are on the right. So researchers from anywhere within the collaborating institutions can access the data and the analytics platforms with a web-enabled device and work with that big data as if it was local to their computer in interactive mode if they like, through either a Jupyter Lab interface or online systems or command systems. Pipelines play a big role in dealing with this data, and we're developing pipelines that enable the end users. They're not in-house built pipelines that describe the way that the data is processed. They're modular pipelines that get deployed on the high-performance system through the cloud, that allow the users to interactively work with any of the elements of a pipeline to customize them to their own research. These pipelines produce the big data products coming out of the Meerkat telescope. And here's an example of a continuum image from one of the large survey projects called MITI. It's like if you tried to produce this image with the VLA, it would take hundreds and hundreds of hours. We did it in about 10 hours with Meerkat. Every object in here is a real object, and it's the beginning of a new era of detecting radio sources. And over the next decade, we will detect 1 billion new radio sources in the sky, both in continuum and in the atomic hydrogen spectral line. It really is a new era in radio astronomy, and with lots of data attached to it. Okay, so the big data aspect of the BRICS ITDN is basically BRICS and the petascale astronomy. And what I've listed here that the 5 individuals on the country co-PI teams that are part of the big data side of this. And so we have basically leaders in big data challenges in the 5 countries that are helping us design and develop the approach to big data. Our broad goals are to build a data network to bring together technologies and expertise within the BRICS community, to solve the technology and data science challenges for this new era of big data, to create collaborations among researchers in the BRICS community, and to build projects for exploration and discovery, to train a new generation of multidisciplinary data scientists, which speaks to the societal benefits that David mentioned, and to realize with those new skills, the opportunities for societal benefit. We have 4 thematic areas within the big data collaboration. The first one is the science-driven aspect, to identify the projects that will be the basically the platforms upon which we build solutions. So these are developed the science collaborations among the BRICS partners. We want to build open science federated cloud environments for collaborative big data research. We want to bring novel algorithms and sort of fourth industrial revolution data science solutions to the big data challenges. And we want to take those challenges and solutions and turn them into societal benefits. So on my last slide, we had a sort of a first planning workshop to discuss the first steps in this collaboration going forward. And as a first step, we're planning to work on building a federated BRICS data intensive astronomy cloud, to build on the cloud system we have in South Africa, to replicate similar cloud systems among the BRICS partners, and to federate that into a single platform environment. So we have a platform to beginning to work together on the big data solutions. So federated cloud environments are something that are emerging around the world. The European Open Science Cloud is a tremendous example of that. It brings together distributed resources from among the European community countries. And we're beginning to think in South Africa about an Open Science Cloud in South Africa as well. So basically, we're going to leverage that technology development to build a platform, a BRICS federated cloud as our first step. So that's, I think, where I'll stop, Dave. I'll stop sharing.
Okay, thank you, Russ, and thank you, David, for this very nice presentation. So now it's time for questions. If anyone in the audience has a question, just raise your hand. We have a question from Shri already, so please go ahead, Shri.
Hi, Shri.
Hi, Russ and Dave. What's good? These initiatives are, as a, let's say, as a contrarian, there's nothing I like than undermining this system, whichever they are. And it's good to see the BRICS undermine the first world. And then after that, we'll have something to undermine the BRICS. And I'm always there to undermine. There's one thing I'm sorry to say is missing from this plan, which is very oriented towards data and facilities. But data and facilities are merely the start. It is not the science. The science only happens when people actually convert that into some results. And having grown up in India and spent most of my life, professional life in a first world country, the biggest difference between the advanced countries and the BRICS as a whole, though there's a huge variation in BRICS, is the quality of science, the ability to do the best quality sciences has many things, and some of them are not met in the BRICS countries. And in particular, I would say, I'll not go all the way to education, the college level, because that really varies in some countries like Russia. It's absolutely excellent. But what's missing really is the graduate education. So let me do a thought experiment. I'll give a student in the BRICS country, a good PhD student, 1 billion radio sources already. I'll pretend to be God, which I like to, and I'll say, okay, write the paper. And that is a big difference. You go to a place like Caltech, the students get a year of amazing courses that they don't get in India, they don't get in South Africa. So unless you have the education part, which brings them up to the snuff in the first world sense, the billion galaxies, yeah, you write some catalog, you write some login logis paper, and that's the end of that. I don't mean to be negative, but I'm being actually, my eyes are wide open when I say these statements.
David, you want to respond or shall I?
Well, yeah, I can just say I fully agree with you that there's enormous challenges. You know, this is a debate that's happened here in South Africa about the quality of university education and the preparedness of students entering PhD programs compared to, you know, well-funded, you know, highest echelons of education like you mentioned, Sri, like Caltech. All I can say is anecdotally that there have been very impressive developments in terms of individuals that I'm aware of who have done forefront research and published, you know, papers that are do stand up to scrutiny and do stand up to competition. But, you know, I fully appreciate what you say, that you know, there is so much more that needs to be done. And I'm the first to say it, that, you know, the education system in some of the BRICS countries, particularly South Africa, I'm not so much aware in other countries. Yeah, it's a challenge, but, you know, we do what we can do. And
oh, wait, no, fine. But let's take the challenge and solve it. So what I'm saying is a component of your initiatives, of this big initiative, should have, I would say, a graduate master's level program by which students can sign up. They can even, I don't care whether it's a degree in the traditional, you know, university granting thing, but something at least recognized within the BRICS consortium. Okay, I've signed up, I've done this, and I have some experience in this. So the last 2 years, I took advantage of COVID, and I organized 2 years ago something called the X-Ray Club. I have, which I urge you to see. It's on my website, actually. If you go to the bottom, it says XC, which is X-Ray Club. And it had about 24 talks by the best people in the world, the PIs, the directors. I mean, anyone in X-ray astronomy gave a talk on this, okay, or anyone who's someone. And then last year I had a UV club, and I invited students from China, basically the Far East, China, Japan, Korea, Taiwan, and then India. It was arranged so that either way, there's some in the morning, some in the evening. The India was always, you know, a fixed point because you'd always choose in this time zone things. So, you know, the attendance varied between 20 and 40. I came to learn a few things. It's just not the content. These are amongst these two sites. And in fact, they're so good that Matthew Bales in Melbourne asked me whether his center could curate these lecture series. But anyway, I can write you a long, thoughtful letter along these lines. Okay.
yeah,
And all I ask you to remember is that you have a Shri in Caltech, the same Shri in India would have done much, much less. Okay. And that's nothing to do with my genes, which are exactly the same, but it's to do with what I was able to learn and what atmosphere I'm in. So until you get that, you're not completed the revolution.
yeah. Look, I think I'll let Russ say something, but you know, one of the things we want to develop is in the societal benefits, look at how we can leverage just some of the things you said. So I think this should be a conversation that we maybe take offline and talk to you a bit more about it, because I would be really supportive of doing something like that. But Russ, do you want to say something?
I'll just echo your comments, Dave. I think we recognize the challenge among the BRICS countries in developing people with the requisite skills to actually make this a success. And so we have identified that as one of our challenges. We haven't articulated the programs yet in that area, so I think, Shri, it would be really useful to have a conversation.
Yeah, well, I will send you a
thoughtful letter.
And last few years, I taught a course, you know, mini course lasting 2 weeks. Choose a topic, you know, develop it from ground up, and in India. And I really came to appreciate the last mile problem is so severe that you can give anyone all the data, and, you know, in the end you'll get a paper. It doesn't mean that those people are stupid. It doesn't mean that Sri in India working would have been stupid. It is just, life is a series of multiplications. And if one of the numbers is close to 0, the answer is 0. One last comment. A lot of I do like the 1 meter and all this, because this all sort of, there's something very resonant about all that stuff. And of course, the radio scene is phenomenal. I mean, and that's partly because it is really leading edge. But the 1 meter stuff, I know a lot of you have to, pay homage to LSST and the usual stuff, but let's get to the real stuff. The 1 meter is better fed by a very high cadence discovery machine and not LSST, okay? Of course, I write a proposal. It says we begin the era of LSST and then go on to do really what should get done. So I think I'd urge this committee to really look into a very powerful discovery machine suited to the follow-up by 1 meter telescopes. And that's not LSST, no matter what spin you want to give me.
Yeah, no, sure. I mean, I think this concept of a network of 1 meter telescopes globally is sort of an extrapolation of ZTF, right? It's like a bigger, more of them to cover the whole sky. And that would be
maybe I should donate ZTF to this cause.
Sorry?
Maybe I should donate ZTF. I mean,
to the cause. Yes.
Yeah, since I've been running it and I want to go and do other things, maybe I should think about that.
Well, yeah, I mean, but definitely this has a life of its own outside of servicing any follow-up for LSST, for sure. Yeah. But
well,
thanks for those comments. Yeah.
Yeah, well, I find it a little annoying that people keep drinking the LSST Kool-Aid and as though the whole thing starts and ends with it.
No, I mean, as you point out, a network which has a cadence of an hour is going to do different signs to
exactly.
a telescope that has a cadence of a week or 5 days or 3 days.
Yeah, you want to undermine the big system by doing something very different. Anyway, sorry, but this is a holiday at least here, and maybe I should shut up now.
Oh, is it? What holiday is it?
President's Day. I tuned in to hear you guys.
President's Day. Which president?
I don't know. They've been changing the names. The holiday.
Okay.
I didn't realize it was a holiday. So yeah, people are really
holiday here as well, but it's a much friendlier when it's Family Day.
Oh, right.
And spend with your family.
Okay, we're sort of really running out of time. So is there maybe another very short question very quickly? We still have time for that. Okay, we have a question from Rachel. Please, Rachel.
Just a very quick one. Firstly, David and Russ, thank you very much for the talk. It was super interesting. And I noticed as you were going through, you mentioned that you have 3 junior researchers who have already started work in South Africa. And I'd like to extend an invitation to them to come and give us a colloquia on their work at some future time. I'd love to hear more about it.
Yes, I've been trying to twist the arm of my PhD student, Hanno Murray, who's working on machine learning and been using the plastic data set to do just that. He's in his writing up phase now, but I think it's well timed he should do that for sure. Yeah.
Excellent. I look forward to it.
Thank you.
Okay, great. So David and Russ, thank you again for this nice talk that you presented to us today. And with this, I would like to conclude the colloquium today, and I will see you in a couple of months.
Thanks very much. Thanks for the opportunity to speak. It was great. Thanks.
Okay, thank you. Bye.
Bye.